robotic arms within the context of FIRST. So what is FIRST? FIRST stands for Inspiration of Robotics, Science, and Technology. It is an organization that hosts an annual high school robotics competition, aptly named the FIRST Robotics Competition. Every January, they give out a game animation which details a game that each FIRST robotics team has to build a robot to complete and compete in within 6 weeks' time. After the 6 weeks, the teams take their robots to the regional competitions, and they go head-to-head. Often, FRC games lend themselves to robotic arms. However, we have never really been able to successfully make one on the Ligerbots, which is the Newton North and Newton South's joint FIRST robotics team, of which I've been a part of for 4 years. So the real question is, what traits make for a successful robotic arm, and how can you design and engineer an arm so that it will have these traits? And I came down to really two sort of properties of a robotic arm that are necessary for its success. First of all, its ease of use for the driver and its simplicity. This was affirmed by Bruce Hockaday and other FRC mentors whom I talked to online. Bruce Hockaday, I specifically interviewed myself over the phone. He is the mentor of Team 173, the Rage Robotics. And in 2007, Rage Robotics had a robotic arm in which it swiveled around on the robot 360 degrees in order to give the driver more ability to grab game pieces on the sides of the robot. And this was a good idea in principle. However, after talking to the driver after the competitions were done, Bruce found that the driver actually said that the turret or the swivel was a detriment to his ability to correctly maneuver the robot, since he had to keep track of where the arm was at all times in relation to the rest of the robot. This made it very difficult for him to be able to pick up objects correctly and efficiently. And so keeping it simple is a very important aspect of designing a robotic arm. Additionally, robustness, or its ability to withstand shock forces, is also an important factor in creating a robotic arm. This was exemplified in 2 years ago when the Ligerbots tried to create 2 robotic arms on our robot, and neither of them worked. The first, which you can see on the left, is the one that I designed and engineered. It is designed to take a minibot that is placed on the end of the arm, place it on a pole, and the minibot is then supposed to ride up the pole about 10 feet and hit a button on the top. The minibot part worked fine. When it was placed on the pole, it would ride it up and it would hit the button, and that would all work. The problem was that when the arm was actuated, it had to be within a 1-inch clearance of the pole, or else the minibot would either jiggle on the pole or it wouldn't even get onto the pole to begin with. And this was too much for the driver to be able to work with from 20 feet away. So that's why my arm did not work. The other arm had a number of reasons why it didn't work, not all as significant as the fact that the driver just couldn't maneuver it. The first was on the left of the arm. You'll see that it had a telescoping portion in which the long box rode along the post at the bottom, and then a smaller sort of cube rode along that box in the middle. That was fine, except for that the winch that activated that telescoping mechanism could only make it be in either an all or nothing position. You could either drive it all the way up and keep it there by applying power to the motor, or you could keep it all the way down by just letting gravity do its thing. Unfortunately, you could never have it anywhere in the middle, because there was no way to correctly put enough power on the motor so that it would just counterbalance the gravity. It was not self-locking, to use a term that I'll use later. Another reason was that the motor that actuated the part of the arm that swung out from the rest of the telescope was simply not really powerful enough to actually withstand the torque force from the rest of the arm. Torque, in case you didn't know, is the rotational analog of force. So if I ever say torque in this presentation, just think of force, or force in some sort of rotational context. Finally, to get at the point of robustness, the arm was not very robust. It flapped around whenever we moved the robot. It wasn't very securely attached to the rest of the telescope, and the bottom piece that actually held the tube in position, it's that C thing at the bottom of the tube in the picture, actually got bent at a 90-degree angle at one point during the competition, and we simply couldn't use it anymore. And so robustness and simplicity are the two most important things when designing a robotic arm. And so I have come up with various design methods that have been able to make for an arm that will have these two properties. The first of which is to have a piston actuated joint near the base of the arm. This allows for you to tailor the arm to its dual purpose. Usually arms in first require you to either pick something up and put something down, usually in two different places. Now these are two similar yet different operations of the arm, and it's good to be able to have the arm be in two different discrete positions in order to do these things. And so a piston, which can either be all in or all out, gives you that necessary binary nature. This way, when the piston is all the way in, the arm can be closer to the ground, so it's easier for the driver to access the objects on the ground, and easier for the driver to access the objects that are farther away from the robot on the ground. And then when you want to place the object elsewhere, usually higher up, you can extend the piston, and then the arm will straighten up, and you will be able to place the object on whatever peg or shelf you need to. Another reason why a piston is perfectly suited for this type of joint is because of the large amount of force that is able to give out onto this joint. A piston is able to build up force by pressurizing air in the air tanks beforehand, and that buildup of energy is able to give a large output of force, which is able to counter the torque of the rest of the arm on that joint. My next design method is a telescoping arm actuated by a lead screw and a Cascade system of cables. But the most important part of this is that it's linear motion. Linear motion is very important in first arms because the driver can simply point and extend an arm rather than dealing with some sort of fancy articulated motion with two rotational joints. The problem with linear motion, however, is that motors always output rotational motion, and the only other way to actuate something on a first team is to use pneumatics, which again, as I said earlier, requires binary motion, which we do not want. We want continuous motion. And so one method of turning this rotational motion into linear motion is through the use of a lead screw. A lead screw, like a bolt, has threads along it, and so what you do is you attach the lead screw to the motor, and you spin the motor, and the nut along the lead screw will travel along it translationally. So that's great. It turns rotational motion into linear motion. The problem with it is that it often is very slow and is able to output a lot of force, even though you really only need a reasonable amount of force, and you need it to go relatively quickly. So you can combat that in one of two ways, or using two ways. The first is to pick a motor to actuate this joint that is, at its beginning, low torque, high speed, which is able to sort of calm down the amount of torque that the lead screw can put out and the amount of speed that the lead screw can put out. And the other is to use this sort of cascade cabling system that I've designed here. There are two cables, one red, one blue in the diagram. They're both anchored at the first and third sections at the same place, and then they both go through holes in the second section on opposite ends. And so when the lead screw is turned, and that pushes the second section out, then the second section holes move out along with it. So say the second section moves an inch, the holes will move an inch, but then the rope also has to move an inch through the holes, which pushes the third section out for 2 inches for every inch that the second section moves out. This doubles the speed at which the third section moves and halves the force that it outputs, which is great to combat the sort of high force, low speed motion of the lead screw. The other great property of lead screws is that they're self-locking, or at least most of them are. You'll obviously, when you buy a lead screw, if you want it to be self-locking, you have to make sure that it's self-locking before you buy it. But that means that if I turn it so much and I stop the motor, then the lead screw will stay in that position no matter how much force I put on the nut in either direction along the axis of the lead screw. It will not force the lead screw to move. It's impossible for it to do that because as you push down more, the frictional force between the nut and the lead screw proportionately increases so that it doesn't actually move. And so self-locking mechanism is very important for arms, as you can imagine, because you want it to be able to stay in a position that you put it once you're done. And so a self-locking mechanism for rotational joints instead is to use a worm gear. Now this is similar to a lead screw in that when you turn the screw with a motor, the gear turns, except when you try to turn the gear with something else, the screw can't turn for the same reason that if you push along a nut on a lead screw, the lead screw won't turn. This means that you can lock the position of an arm in a certain position, even if it's precarious in some sort of fashion. And that allows you to keep an arm in a position that you might want to score in, or you might want to pick up objects off the floor in. This is great for robotic arms for that reason, and in addition that usually they entail high gearing ratios in small amounts of space, rather than normal systems of multiple gears attached to one another. This was used by, for example, Team 111 in 2007, I believe, and they were able to successfully use it for different purposes to keep their arm in the correct position. And so that worked out very well for them. And so now that we have the joints that we want to figure out how to actuate, and we know what they are, we have to pick the motors that are going to be able to correctly and efficiently actuate them. So motors act by having a certain stall torque and a certain free speed. Stall torque is in the diagrams is tau sub stall, and the free speed is omega sub free. When you actuate a system, it usually requires a certain torque required, or a certain torque that is required for it to actually actuate it at all. And when you actuate it with a motor, it takes the percentage of the torque required divided by the torque stall. It basically takes how much torque you're actually using out of how much torque you have available. You take the rest of that and you multiply that by the free speed to get the actual speed that the motor runs at. And that's exemplified in the first equation I have up here, where I say the actual speed is equal to the free speed times 1 minus the torque required over the torque stall. And then things get interesting when you write the speed at which the motor runs as a function of the gearing ratio of the gearing system that you use to separate the motor from the system that you're actuating. A gearing ratio of R to 1 means that you will gear down your free speed by R, and you will gear up your stall torque by R. So if I replace the free speed by R the free speed divided by R, and the stall torque divided by the R times the stall torque in the previous equation, you get the second equation up on the board, which gives the speed at which the motor runs as a function of R, the gearing ratio. And if we take a look at the graph of that, which I've also shown on the board, you'll see that there's a single clear maximum point to that graph. And it's a relatively simple calculus problem to figure out what the coordinates of that point are, and they're written at the bottom. The best possible gearing ratio is equal to 2 times the torque required over the stall torque, and the maximum speed at that gear ratio is equal to the free speed times the stall torque divided by 4 times the torque required. This allows you to take a motor and a given system that needs actuation and tell how fast that motor is going to actuate it, and tell at what gearing ratio it's going to best actuate it. And this can help in your search for the right motor, because first gives you a list of motors that you can use. You can't go beyond that list. So you can, first of all, perform this calculation on any candidate motors from that list, and then figure out, okay, what speeds am I going to be actuating this at with this motor? What required gearing ratios am I going to have? Is that gearing ratio feasible to do in this type of environment? Is that speed enough? Is it too much? And so you can figure out what motor is going to be perfect for the job using these calculations. And so my final design method is to use a sort of hybrid end effector. Usually end effectors, which are basically the hands of an arm, come in a sort of C shape. Usually they'll be either an active type, where they'll use conveyor belts to funnel in the objects into the grabber, or they'll be a clamping type, where they'll actually go and clamp onto the object in question and then bring them somewhere else. And they each have their merits and disadvantages. The active type is great because you can easily pick something up. You just need to basically get where it is and then it'll be funneled in. The active type, however, the clamping type, however, you need to sort of get leverage under it initially to be able to grab onto it, which can be difficult. However, once you've grabbed onto it, the conveyor belt type doesn't hold onto it as sturdily as the clamping type does, and so it can be prone to either falling out or misaligning, and so that can often lead to the failure to gain as many points as you might want to from putting the object in a certain place. Whereas in the clamping type, usually you'll be able to put it in the right place. So my proposal is to use a sort of hybrid type where you have the conveyor belt system at the bottom and the top to actually pull in the objects, but then you have that red flap at the end to come down and enclose the object to keep it in place so that it doesn't fall out while you're moving the arm. And so those are my design points, and now I would like to show you the CAD drawings that I've made of the robotic arm over here. Let me just plug this in. CAD stands for Computer Aided Design, which is many programs allow you to do computer aided design. Basically, you model each part of the arm or the object or assembly in question, and you place them together, and this allows you to figure out how things are going to fit together and how things are going to measure up against each other. Make sure that you have enough room for everything. Make sure that you know exactly what you need to get before you go and buy parts. It saves you money, it saves you time when you're going to build them, and most first teams and all professional engineers use computer-aided design to model all of their systems. As you can see here, I have my piston actuated joint. Here's the piston. Here's the rest of the arm. Here are the bases for the arm. Here I have my end effector. You can see the conveyor belts and the flap that goes down and encloses the object in question. Here I have a lead screw with a motor that's actuating this telescoping system, which I labeled in 3 different colors so I could easily see the difference between the 3 sections. And here I have a worm gear gearbox that allows this arm to be put into a specific position and kept there. And then I would have chain over here, but there's really no way to model chain in CAD, and there's really no need to, so it's not there. So that's my CAD model. And finally, here's my final product that I've designed and built. It has everything on here except for the end effector. Unfortunately, that would have required access to a machine shop, which I didn't have while I was building this. But it has all of the other points. It has the pneumatic system that actuates the initial joint here. It has a worm gear gearbox that actuates this part here, and then it has a lead screw here in order to push this telescoping system in and out. So to demonstrate it, be warned, this is going to be loud and quick. So a team may initially want to extend this so that they can grab something off the side of the robot, so they might do this. Not that much. In an actual competition situation, a team would have programmed this so this motor wouldn't have gotten as much power as the rest of the motors would, and maybe gotten 75% power or something like that. But as you can see, I've maximized the speed at which this motor can run, so that it runs as efficiently as possible. So I'm just going to reverse that. So you might put it into this position so that you can then grab something and then extend the telescope by pushing out the lead screw, and then you might grab the object, pull it back in, and then you might want to push the entire thing up so that you can get it in a position where it actually is able to place the object on someplace high. So I'm going to pressurize the pneumatic system. This would have been done already, so I would able to be able to just hit a button to actuate the entire system already. But first, I just have to pressurize the pneumatic system. So I've pressurized it to 40 psi, or pounds per square inch. That means that in each of these 3 air tanks, a square inch of air in there weighs 40 pounds. And now I'm going to switch the piston's position so that it is all the way up. Oh, sorry, wrong one. And now a team might go and actuate this further up so that it can place something on a shelf or a joint or something. So again, it goes very quickly. Oh, unfortunately, the chain has come off. That occasionally happens. All right, that should work. Unfortunately, apparently, I did not make that chain long enough, or sorry, short enough so that it would be taut with this sprocket here that holds it. But that will be fixed before the competition happens. Anyway, a team would then extend the arm the rest of the way and pull it back in order to then keep going with the rest of the game. And then it would maybe depressurize the pneumatic system so that this can then fall back down and then continue. So this is just the tip of the iceberg when it comes to robotic arms. First is obviously a high school program. Robotic arms have many applications in industry, for military purposes, to defuse bombs, for surgeries to make them safer so that you don't require as much movement as you would with a human hand. Dean Kamen, the founder of FIRST, created a 14 degree of freedom, which means that it has 14 joints in it, robotic arm to be used as a prosthetic for Army veterans or anyone else who has lost a limb in whatever type of accident. And so robotic arms have endless possibilities, and this is really just the beginning. So thank you. Yes?
I was wondering if you had a specific game in mind when making the arm.
I was trying to make it so that it would follow that game from 2 years ago where you had to take a tube from the ground and then place it on a peg on either side of the field. The highest peg would be 9 or 10 feet high, and you would have to be able to place it there or at other heights to gain as many points as possible. So, anyone else? Yes.
So how long did it take you to design and then build, and did you have any prototyping steps in between, and what did you do in those prototyping steps?
Designing took about 3 weeks, building the CAD model, coming up with the ideas. And then building actually took a month to get the parts, put them together, actually get everything to actuate correctly. And in terms of prototypes, I didn't really have many prototypes. I tried to minimize that since I was working with a certain time frame. I was trying to figure out what would be the best ideas based on past designs that I've looked at from first teams that have worked from robotic arms that have worked from first teams in the past, and trying to figure out whether my design worked or not in CAD. So that CAD that you saw was the last of a long set of iterations of designs that I went through during the whole process. So, yes?
The graph you showed for
yeah, here, I can get that up.
Where did that chart come from?
I made it myself in a program called Wolfram Mathematica.
All right.
I don't know if you've heard of it.
The data just came from those equations?
Yes, the specific data for this, I used, I think, what was called a window motor, and I used, I think, this joint here on my robotic arm for the torque required, and then that is a graph of the speed versus the gear ratio for that that motor. So.
You're actually designing this for a competition that's coming up?
It was a competition that was 2 years ago. This is more of an intellectual exercise rather than to actually be used in game. But it could have been used in game. Is the whole idea of it. So.
And is it something you're supposed to control with other kinds of controls? I mean, it seemed very cumbersome to.
Right. My entire project was mainly about the mechanical design and building and that sort of nature of the arm. There's the entire other aspect on an actual first team in which you would go through wiring everything up to motor controllers and up to a computer that's on the robot, and then programming that to be able to take commands from a computer that's on the sidelines. But that wasn't really within the scope of my project. So I'm just touching leads on a battery to the wires, but in an actual first game, you would be able to control it more precisely using code and using an actual controller. So.
Time for one more question.
What are you doing next year?
Next year, I'm going to MIT.
Never heard of it. Congratulations.
Thank you.
How did the senior project maybe stretch you as a student or as a person?
I've never really had to work on an independent project like this before. It was really interesting to be able to also engineer and design something on my own. I've always done it with other people. It's never been a sort of me by myself project. So that was really interesting. Yeah.
Learn anything about yourself?
About myself, I guess that I am a slightly better designer than I am a builder. I made more mistakes than I'd like to admit in the placement of holes and cuts and things like that. So, no problem. Thank you.